All right, good morning, everyone. Let's continue discussion on chapter 3 and look at the physical construction of an inductor. So, inductor is nothing but a spiral coil of a conducting wire. Each loop that you see in here is referred to as a turn. Okay, so a loop of an inductor is referred to as a turn. And the number of turns in an inductor is given by the uppercase letter N. So the equation for a inductor is given by this: L equals mu N square A over L. Uppercase L is the inductor. Lowercase l is the length of that inductor measured from end to end of that spiral coil. Okay, end to end of the spiral coil. So it looks like a 1, but it's the length of that inductor. A is the cross-sectional area of each loop or each turn. Okay. And the A, of course, can be determined from the radius of each loop. And this is, of course, assuming that each loop, has the same diameter. And the unit for inductor is, of course, henries. Mu, yes, question? WB is the unit Weber. So there are actually many units depending on the author, depending on the field of study. They would either use Weber or they would actually use the physical quantities associated with it. Like, so voltage, current, for instance, they are named after people, right? Voltage is named after volta, current is named after ampere. But actual current definition is the rate of flow of charge, so coulombs per second, but it's simply referred to as ampere. So in that case, or in that sense. Anyway, mu is the permeability of the material. Permeability basically describes the ease with which magnetic flux lines can be established inside a material. Okay. Remember, a couple of slides ago, we showed the working principle of an electromagnet. And yeah, the image before that, I showed an inductor similar to this one, which did not have any material inside it. So the empty space inside a spiral coil is known as the core of that inductor. Okay, this is known as the core of that inductor, the core of the spiral. If you insert a magnetic material or a material which has high permeability, then we call that, then that enhances the magnetic field strength, because the high permeability allows the magnetic flux lines to be established with ease. Okay, so mu again is the permeability, and it's given by the product of mu 0 and mu r. Mu 0 is the absolute permeability, or the permeability of free space or vacuum. It's a constant, and the constant has a value of 4 pi into 10 raised to minus 7. Oh, units, Weber per ampere meter. Magnetic flux, Weber. Flux density, the number of lines per unit area, is named after, I mentioned this last class. Anyone remember? Tesla. Magnetic flux density is named after Tesla, 1T. Okay, let's see. Mu 0 is, as I stated, this is the permeability, free space. Mu r is the relative permeability of the core material. Okay, that's a material property. It is simply a ratio. It is measuring the permeability of that material relative to mu0. All right, relative to mu0. And so it does not have any units. It is dimensionless. It's a ratio. So it is unitless. It does not have any units. Some examples of real-life inductors. These are about the same size or similar size as resistors. And the ones in the top row are in the shape of a toroid, so they are known as toroidal inductors. Okay, toroidal inductors. I just wanted to point out a couple of things. If you look at the thickness of the coil, that illustrates the current carrying capacity of that inductor. Thickness of the coil doesn't have anything to do with the inductance level, okay, but it has everything to do with the current carrying capacity. The thicker the wire, the more current it can carry. The thinner the wire, the less current it can carry, right? That's the operating principle behind an electric fuse. A fuse is made up of a thin wire going from one end to the other. It has a certain current carrying capacity. If the current flowing through that fuse increases, then we say that the fuse blows out, the fuse is short-circuited, right? What happens is basically the thin wire, if the current carrying capacity exceeds that of the thin wire, it simply heats up and disconnects or blows up. It's kind of the same principle. Look at the number of turns. N is less. If N is less, the inductance is less. If N is high, inductance is high. And you see that reflected in these values here. 10 microhenry versus 1 millihenry. 100 times as much. Look at the current carrying capacity, 10 amps versus 1.3 amps. Thick wire can carry a huge amount of current, where 10 amps, by the way, is a huge amount of current. Typical electric and electronic circuits, the current is on the order of milliamps, sometimes even microamps, very, very small. So 10 amps is a huge amount of current. And then lastly, if you look at this one, it has the exact same value. There's the exact same value as the one shown in the middle, 1 millihenry. But the current carrying capacity is a little bit larger. Okay. The reason for the low inductance value is that the length of the coil, L, is longer. The equation, L, inductance value is inversely proportional to the length of the inductor. So the longer the length, the lower the value of the inductance. Okay. All right. So that was just a few examples of real life inductors. Let's get to the VI equations. Okay. We won't go too much in depth, right? We'll look at the voltage and current equations, then we'll look at the power equation and the energy equation, and that would be it. So remember I said the inductor operates on the principle of an input current. If the current changes, we can measure a voltage across that inductor, across the terminals of the inductor, right? So it's directly proportional to the rate of change of current, di over dt. Voltage across an inductor is directly proportional to the rate of change of current, di over dt. Okay, if I changes, then when we say the rate changes, of course, and so voltage would appear across that inductor. So the equation managed by a constant, the constant is the inductor value itself. So V equals L di over dt. V equals L di over dt. That's where the equation would come from. Okay. Now, if you want to find the current given the voltage, you simply integrate. So V equals L di over dt. Integrate both sides. L is a constant. You take it outside, take it on the other side, and you get 1 over L integral of V equals the current I, which is basically the IV equation. And I will explain what each term of that equation means. Okay. All right. So remember I said if you apply energy to a capacitor or an inductor, the energy cannot transfer instantaneously. It takes a certain amount of time for the energy to be transferred. So if you apply a current of, let's say, 1 amp to an inductor, 1 amp is here, the inductor current cannot go from 0 to 1 instantaneously. It follows an exponential pathway, right? It takes some time for the current to reach that point. So x-axis is time, and let's say we apply a voltage or a current that is constant, DC or fixed value, meaning it does not change its value with respect to time. So an inductor it takes some time to reach that point, that maximum point, okay? So the voltage and current for an inductor and capacitor are functions of time. And so oftentimes you would see the equations for IL or VC or VL. L stands for inductor, C stands for capacitor. So since they are functions of time, you would see V of t, where time is the variable, and you would see I of t, current as a function of time. And that's all it means here. Time t is the variable. Now the transient portion where the energy transfer is taking place, we look at those equations in chapter 4. Okay, we look at those equations in chapter 4. But here, since we are talking about voltage and current as a function of time, let's take a look at this equation right here. 1 over L, of course, it comes from the constant being on the other side of the equation. Simply look at this right now. We are integrating the voltage between two time periods. Integration, simply stated, is simply summing up everything between two time periods, right? Between two endpoints. We take individual slices, which is dx, right? In this case, it's dt, and then we add up all the slices. So we see the limits of the integral going from t0 to t. 0 is always the beginning point, so t0 is the beginning of time. Not literally. As an example, let's say you're analyzing a system. Okay, you're working with a system and the time is from 0 to 10 seconds, let's say. Okay. For your analysis, you could break up this time period into multiple parts, whether 10 parts or 100 or thousands, doesn't really matter. For convenience sake, let's just say we are analyzing a system from 5 to 7 seconds. So T0 simply references the point in time at which you begin your analysis. Okay, T0 is the point in time at which you begin your analysis. So in this example, if a system that you're looking at is going from 0 to 10 seconds, and you wish to analyze a small portion of that system, you're looking at, let's say, from 5 to 7 seconds, then the 5 represents T0. And then you're analyzing until 7. So T would be 7. But T0 to T in this case, when you solve for the equation and you plug in the limits of the equation or the limits of the integral, it will go from 5 to 7. Let's take a 10-second pause while you think over that. Let me know if you have any questions. Does it make sense? T0. Okay, T0 is the initial point, the point at which you begin your analysis. Speaking of initial, there are many authors or many books which like to use the term I. I for initial. So you might see something like TI. I don't like to use I because I is used for current. Okay. But when we get to chapter 4, sometimes you might hear me reference the word called initial time, and initial time simply is T0. Okay. So we are simply integrating the voltage from time T0 to T. T is a variable that allows us to find the value of that voltage or current at any given point in time. And lastly, we have this term, I of T0. It simply means the initial stored energy in that inductor. Okay. Simply references initial stored energy. Remember, we are analyzing the same example. We are analyzing or beginning our analysis at 5 seconds. So we have to include the energy that was stored in the inductor before 5 seconds. It could be 0 or it could have some value, but we have to account for that value. That value would be a constant value. It would be given to us in the problem statement itself. It would be your job to recognize the information and then extract that value from that problem statement. Right? Does that make sense? Any questions? Any questions at all? Okay. Moving on, what does that equation mean for a DC or a constant source? So this represents, this is a fixed value or DC source. What do we see? It cannot change in an instant. It cannot go from 0 to max value in an instant. It charges, right? The charge follows an exponential waveform. Once it reaches that maximum value, what happens? It stays there. The energy is transferred, right? Until it releases back into the circuit, but it stays there. So the value is steady with respect to time. And hence that point in time is referred to as steady state. And when it reaches maximum charge, when it reaches steady state, voltage drops to 0. If voltage goes to 0, means that the inductor behaves like a short circuit. Okay, inductor behaves like a short circuit. You apply 1 amp of current to that inductor, it reaches 1 amp. Until it reaches 1 amp, there will be some voltage that appears across that inductor. But once it reaches 1 amp, that voltage slowly drops to 0. If after a certain amount of time, that 1 amp goes to like 2 amps, then again, the voltage would appear across the inductor. But once the inductor reaches 2 amps, that voltage would again fall to 0. And then it keeps going on, so on and so forth. But as long as the current is constant, the voltage remains at 0. Mathematically speaking, V is L di over dt. If I doesn't change, di over dt is the rate of change of, or rate of flow of current, right? Di over dt as a function of time. If it doesn't change, it's a constant, then di over dt is 0. Voltage is equal to 0. So mathematically speaking, V goes to 0 if di over dt is 0. So an inductor at steady state behaves like a short circuit. When we get to capacitor, you'll realize capacitor is the dual of an inductor, so the equations are very similar and opposite also in many cases. So equation for capacitor is C dV over dt. The capacitor behaves like an open circuit when it reaches steady state. So exactly the opposite of an inductor. Electrical power is simply the product of the voltage and current. You plug in the equation for the current, for the voltage, di over dt, and you obtain power for an inductor as Li di over dt. Okay, Li di over dt. And then there's a derivation, few steps, where you plug in the values and you obtain an expression for the energy. This should be lowercase energy is half Li square. So this is the total energy stored in the inductor. Okay, half Li square. Half Li square. And those are the only equations that you need to worry about. Okay. Again, you do not have to memorize these equations. You can have them on your equation sheet, but you should be able to recognize and know how and when to use them. All right. Oh, any questions before I move on to the capacitor? Any questions at all? Any questions? Okay. Capacitors are nothing but two parallel conducting plates separated by an insulating material. Okay. So conducting plates separated by an insulating material. An insulator. Okay. If you put your two palms of your hands together, it's separated by air, two conductors separated by an insulating material. And if we had a meter capable of such measurement, we would be able to measure the capacitance in the palm of our hands, literally. Okay, so any two conducting plates separated by an insulating material is a capacitor. It has the capacity to store energy in the form of an electric field or in an electric field. The symbol is simply noted by two lines or two parallel lines, okay, of equal length. Sometimes that line is curved, concave, and this is something I didn't. If you have an arrow passing through a component, that arrow simply notes that the value is variable. You can change the value of that inductor, capacitor, or that resistor. Okay, it simply means it's variable, which is what you would do if you would, if you were taking 251 and use one of the yellow boxes in there, you can change the value of the decade box. You can represent it as a variable resistor. So an arrow passes through a component. It means the value of that component is variable. It can be changed. Okay. All right. So that's the physical construction. Let's look at a little bit of the physics of the working of a capacitor. Okay. A, B, C, D. Each image is simply showing the initial state, then the final state. Okay. So the first one is showing you that you have a capacitor that is completely discharged, meaning completely zero, doesn't have any charge across it, any voltage across it. And then it's connected to a voltage source with a value of Vs. Okay, value of Vs. This voltage source is connected to the capacitor. When the switch closes, it allows a pathway for the voltage source to be connected to that capacitor. So what happens then is that the electrons in the wire and the plate of the capacitor are attracted by the positive charge of that voltage source. So they start flowing in a, what am I saying, clockwise direction. You might just start flowing in a clockwise direction. No, I'm actually doing the other way around. Counterclockwise direction for you. Okay, so it's flowing in the counterclockwise direction in the illustration. At the same time, at the negative end of that voltage source, electrons start flowing in this direction because they are being repelled by the negative charge or the negative end of that voltage source. And so slowly but surely, charges get built up on each end of that parallel plate. Okay. When an electron leaves the plate, it leaves behind an excess positive charge. Absence of an electron is equivalent to a net positive charge. Okay. So when an electron with negative charge moves out, now the total number of positive charges are unbalanced, and you have one extra positive charge for every electron that leaves. So you have a buildup of positive charges on top and a buildup of negative charges on the bottom plate. The key to the operation is that the two plates are separated by an insulating material. So the electrons cannot cross over or cross through. Okay, they're separated, so the electrons cannot cross through. This is very important to understand. Since they cannot cross through, the charges are built up across those two plates. The difference between those two charge levels can be measured as the voltage across that capacitor. And that is referred to as the capacitor voltage VC. Does that make sense? The electrons are not crossing over from one plate to the other. Now, even though the electrons are not crossing over, they are still flowing from one end of the voltage source to one end of the plate. This continuous movement of electrons is referred to as current flow. Current flow of the circuit. Even though electrons are not crossing through the capacitor, we still refer to that as current flowing through the capacitor. Okay. Again, I repeat, even though electrons are not physically crossing through the capacitor plates, we still refer to it as current flowing through the capacitor. I want to make sure everyone understands that. Okay. And that's as far as we go into the physics of capacitors. Okay, we won't go much in depth. Yes. No. Current is still, because anytime electrons flow, current is flowing. Physically, if the electrons are flowing, that means there's current flow present in the pathway. So even though it's not crossing through the plates, it's still current flowing through the capacitor. And the reason is because there is a charge imbalance. There is Vs on one side, which has some value. And then we have capacitor voltage on the other side, which has zero volts value. So as long as there is a charge imbalance, electrons will flow and we will have a capacitor voltage. Eventually, a state of balance will be reached where Vc equals Vs. And the point where Vc equals Vs, we refer to as a fully charged capacitor. Fully charged capacitor. And that point, electrons will stop flowing. Okay, at that point, the electrons will stop flowing, current goes to zero, and the capacitor is fully charged. It has reached steady state. If the voltage Vs changes, then current will start flowing again and until it reaches steady state again. Similar to an inductor. In an inductor, as long as the current flows, we have a voltage across the terminals. In a capacitor, as long as there is voltage that is changing across the capacitor, we'll have current flow. But once the capacitor reaches the fixed value of that voltage, current goes to zero. In an inductor, voltage goes to zero. In a capacitor, the current goes to zero. All right, any questions? Any questions at all? We can remove this capacitor from the rest of the circuit. If we remove it from the rest of the circuit, that capacitor will hold the charge indefinitely, like a battery. Remember, theoretical analysis always deals with ideal components. Okay, so ideal capacitor will hold the charge indefinitely. In real life, the capacitor will actually discharge through the insulator itself. We use the term separated, right? We say the two plates are separated by that insulating material. But that statement also means the two plates are joined together by that insulating material. Make sense? Right? If the two plates are separated by that insulating material, they're also joined together by that insulating material. So in real life, an insulator will never be 100% perfect. There'll always be a charge loss through those plates. And this allows the charge to be discharged between the two plates through that insulator. Real life insulator will discharge that capacitor. And same thing for an inductor also. Yes. Yes, that is correct. When it is discharging, the capacitor will act as a voltage source, and an inductor will act as a current source. Basically, both of them store the energy. So when they release it back into the circuit, they act as sources. As I said, we can remove a fully charged capacitor and you could short out the terminals. If you short out the terminals, you'd expect to see a small spark because all of that stored energy is released in an instant, right? So it's always safer to use a resistor. You always want to insert a resistor in the middle. The resistor will dissipate the energy in the form of heat, right? Resistor will control the current flow. If there is no resistance, then R value is 0, current goes to infinite or current goes to infinity, and then all of that energy is released in an instant. You see a small spark. If you take a huge capacitor, big cylinders with hundreds of volts, you would probably see an explosion. So it's always safer to use resistors. All right. Just a few brief examples. Remember, the word capacitance comes from the capacity of the component to store energy, right? So it stores charge, and that stores charge for every unit of voltage applied. So Q over V. So capacitance C is simply the capacity to store the charge for every unit of voltage that you apply to it. So C is Q over V, or Q equals CV. And of course, from there, we get the VI equation, because dQ, rate of flow of charge, is current I. So I is C dV over dt. Anyway, that's getting ahead of the equation. Let's just focus on this slide for now. Q equals CV. So 3 simple examples just to show you the relationship. If we take a look at the first one, we see that the capacitor stores 6 coulombs of charge for 2 volts applied. Means it has a capacity of 3 farads. So for every unit of voltage applied, it can store 3 coulombs of charge. Okay. Again, I mentioned this. The unit of capacitance is named after Faraday, so farads. Technically, it's of course charge over voltage. If you increase the amount that it can hold, 12 coulombs, now the capacitance, you need a larger capacitor, right? So it's 6 farads. A farad, by the way, is really huge. Okay. Capacitors are on the order of like microfarads or nanofarads or even smaller than that. Typical capacitors are labeled in microfarads, 10 raised to minus 6. So 1 farad capacitance is actually very, very big, like big cylinders. And then if you increase the voltage, the applied voltage for the physical capacitor, then the charge storing capacity goes down. Okay, so the capacitance value decreases. So if you look at the same example, 12 coulombs of charge, but now you want to apply a higher voltage, a high voltage application, we say that the capacitance value is lower, 1.5. Okay, 1.5. This is just 3 simple examples to show the relationship between charge, voltage, and capacitance. Okay. Physical construction of a capacitor is given by the equation C epsilon A over D. Greek letter epsilon, epsilon A over D, and that epsilon is given by the product of epsilon 0 and epsilon R. Epsilon 0 is a constant, is the permittivity of free space, permittivity of vacuum, farads per meter. And epsilon R is the relative permittivity of the material of the insulator. Relative permittivity of the material of the insulator. And again, similar to mu R, it is relative to epsilon 0. Okay, so epsilon R is a ratio measured with reference to epsilon 0. So it doesn't have any units. It's dimensionless, it's unitless. D is the separation between the plates. That's the distance between the plates. And A is the cross-sectional area of the 2 plates. Okay, A is the cross-sectional area of the plate. But important point to note, a capacitor is 2 parallel plates separated by an insulating material. So if you have 2 rectangular plates, for instance, separated by an insulating material, the only place where you have 2 plates is the overlap. So this is the only area we would look at, area of overlap. We do not have a capacitor in any of the other areas, only in the places where the two plates overlap. This is a real life example from a microchip. Okay, microchips are nothing but PCBs in a miniaturized microform. Okay, you have multiple components and you have wires running all across the place, making a connection from A to B, from C to D, E to F, and so on and so forth. You have billions and billions of transistors in a very tiny amount of space. And to make the connections between all of them, you run wires which are completely flat from one end to the next. And so there are multiple levels. You could have crisscrossing wires going up to like 10, 12, 13, 14, 15 levels of wires. Each of these wires is separated by an insulating material. It's like a bridge. You have a bridge going from A to B, then you have an insulating material on top, and you have another wire going on top of that insulating material from C to D. So at every point where there's an overlap, you have a crossover section separated by an insulating material. It causes the appearance of a capacitance, a very, very tiny capacitance, femtofarads, or even smaller, 10⁻⁻15 and less. But when you have billions and billions of these sections, your signal could get crossed out or short-circuited any point in time or any point in the circuit. So again, it's a real life example, and it's a very big hindrance and a very big point to consider during chip design. Okay, which is basically the area of the overlap between two plates. Okay, so again, physical construction of a capacitor is given by the equation C equals epsilon A over D. A is the cross-sectional area of the two plates. D is the distance between the two plates. And the insulating material contributes to epsilon R. So let's see. Actually, the previous sections I stopped here. So I'm also going to stop at this slide. If you have any questions, I'm available, but we'll end class at this point and pick up here again on Friday. Topic of chapter 3 has been introduced, so please take a look at the homework. Push it back to either Sunday night or Monday night, depending on how much we cover on Friday. All right.